Consider now a slightly different example than the previous one. In this case, the transmission line is terminated with an open circuit, some impedance whose magnitude is equal to infinity. And the length of the transmission line now is 3/8 lambda as opposed to lambda over 8 as it was in the previous example. But like the previous example, the goal of what we seek is the normalized input impedance for this one-port structure, a one-port structure consisting of a length of lossless transmission line terminated in an open circuit. To do that, of course, we can use a Smith chart. So the first step here is a little different than usual in that we're not looking for a contour of constant resistance and a contour of constant reactance and looking at the intersection of those 2 points to identify the load impedance. In this case, the load impedance has a magnitude which is infinite, and there are an infinite number of impedances of this value. Fortunately, they all map to the same point on the complex gamma plane, that of the open circuit, and it is, of course, one of the most fundamental, or perhaps the most fundamental point on the Smith chart on the complex gamma plane, the location of an open circuit. So we merely put our pencil on the Smith chart at the value of gamma equal to 1 to begin. That is the location on the complex gamma plane of an open circuit impedance. So we've transformed our load impedance of infinity into a reflection coefficient of +1. And now we're going to parametrically plot the reflection coefficient on the complex gamma plane on the Smith chart. And we're going to do that by moving up the transmission line toward the beginning. When we do that, once again, the position index z is decreasing, and because of that, the angle of the reflection coefficient is decreasing, and because of that, we are moving in a clockwise direction around the complex gamma plane, around the Smith chart. How far do we move? Well, we move a distance that's associated with our transmission line length of 3/8 lambda, and we're going to use our outer scale values to determine how far that should be. So what we're going to use is since we're moving away from the load and up toward the input, we're going to use the wavelengths toward generator scale on the outer scale of our Smith chart. And again, this is just an electrical index, a value in terms of wavelength, and the benefit of using the wavelengths toward generator as opposed to wavelengths toward the load is that as we rotate in the clockwise direction, which we know we're going to be doing, this index increases in value, and so we sort of avoid having to deal with minus signs. All right, so we take a straight edge and we draw a line from the center of the Smith chart through the point where the open circuit impedance is, or open circuit reflection coefficient, and we continue so it crosses the outer scale. And we notice that in the wavelengths toward generator scale, that value where the yellow line crosses is 0.25, or in other words, 0.25 wavelengths are 1/4 wavelength. What does this mean physically? It doesn't mean anything. Again, it's just an arbitrary number, just like a mile marker along the interstate highway. So we start at this value of 0.25 lambda on our outer scale. Again, just an arbitrary point. The way we use this is we know we need to move clockwise around the Smith chart a distance of 0.375 lambda. So we take the original marker value of 0.25 and we add the length of our transmission line to it, 0.375 lambda. And when we do that, we get a value of 0.625 lambda. What does that signify? Well, that is the value of the outer scale marker that we should stop at. We rotate around clockwise until we come to wavelengths toward generator on the outer scale, a value that is 0.625 lambda, and then we stop. Or at least that should work. The problem is there is no outer scale value of 0.625 lambda. What we find is the largest value we run into is 0.5. We start at 0 and rotate all the way around the Smith chart, and we come to a value of 0.5, or half lambda. And of course we know that as we move a half wavelength along our transmission line, then we are moving 360 degrees around our complex gamma plane. The reflection coefficient function is periodic with respect to lambda over 2. If we move a distance of lambda over 2 in our Smith chart, we're going to come back to exactly the same impedance and exactly the same reflection coefficient function. On a Smith chart mapping, we come back to the same location. So that's why it begins at 0 and stops at 0.5 when it gets back to that same point. Yet the mile marker value we're supposed to be looking for, the outer scale value, is 0.625. So what do we do in this case? So we begin at our marker value of 0.25, and we rotate clockwise. We travel down the road until we get to, metaphorically, the state line. We get to this boundary. And we get to the boundary, the value of that index is 0.5. And so how far have we moved by rotating in this far? Well, we started at lambda over 4. We ended at lambda over 2.5. The difference between the two, is 0.25 lambda. So the distance we've moved from the initial point to the point where we hit this boundary is a value of 0.25 lambda. That's our first step, a distance of 0.25 lambda. The question then is, how much further do we need to go to complete a distance of 3/8 lambda? All right, when we get to the, again, this transition boundary on the outer scale, it gets to 0.5, and then it restarts again at 0. And so this is now going to be our initial marker for the remainder of our journey. We've crossed over the state line, the mile markers values have reset back to 0, and so now we need to keep going. And the question is, how far do we need to go? How much further? Once we determine that, we add that distance to this initial marker of 0, and that will tell us the marker at which where we need to stop, the outer scale value where the rotation should end. So we need to move a total distance of 0.375 lambda. As we rotate halfway around the Smith chart, we of course moved a quarter wavelength. As we move a quarter wavelength, remember the value of the reflection coefficient will be multiplied by a -1, rotating to the opposite side of the complex gamma plane, the Smith chart there. So no surprise there. The remainder, then, that we must travel, if we need to go 0.375, and we've already traveled a value of 0.25, we could take the difference between the length, 3.75, and the first delta, that should be actually delta Z1 there, which is 0.25, and we find we have a remainder left of 0.125 lambda. We need to go 1/8 more of a wavelength before we end our journey. And so to determine at what marker on the outer scale we should stop rotation, we begin at the index of 0, and we add the delta Z2 of 0.25 to it, 0.125 to it, rather, the index of 0, 0.125 to it, and that will give us then a value of 0.125. This 0.125 is the value of the outer scale marker. So we rotate until we get to that point. So we rotate around, and we find here on the wavelength torque generator, right about here, we get a value of 0.125 on that outer scale. We mark it with a pencil, and then we take a straight edge and we draw a line from the center of the Smith chart outward to that mark. So just to summarize here, again, we began at the end of the line where the load is, and we're trying to move back up the transmission line a distance of 3/4 of one wavelength. And to do that, what we did was first move up the line a quarter wavelength, which brought us from an index of 0.25 to an index of 0.5. All right, they start at 0.25 and we get to 0.5 when we move a distance of 0.25 lambda. We stop at that point because 0.5 lambda is the highest value of that outer scale. And then we reset to a new value on the outer scale at that same location, 0, and then we move the remainder of the length back toward the input, and the delta between what we moved the first time of 0.25 and the distance we need to move of 0.375 is 0.125. So we add 0 to 0.125 and 0 to 0.125, and that gives us the value of the outer scale where we need to stop, in this case 0.125 lambda. And here's the graphical representation of what I just said. There's a typo here. There should actually be Z1 and not Z2. The first step, we rotate around a quarter of a wavelength, and then we rotate then an eighth of a wavelength. And that gives us, of course, 3/4 of a wavelength around the Smith chart. 3/4 of a wavelength from the end of the line where the open circuit load is all the way back to the input of that terminated transmission line. So what we're going to do now is parametrically plot our reflection coefficient function, beginning at the value of gamma L and ending at the value of gamma N. And to do that, of course, we strike a circular arc in the clockwise direction. And now that we have the boundaries, the two yellow lines on our Smith chart, where we begin the rotation and where we end the rotation, then we can now execute that operation. So here graphically is a demonstration of that last procedure. We take our compass, we put the pointy end at the center, we put the pencil end right here at the open circuit, and now we strike a circular arc, in this case a radius of 1, and we start here at the yellow line where our index was 0.25 on the outer scale, and we rotate all the way around until we bump into this yellow line corresponding to an index of 0.125 on the outer scale. And then we stop as soon as we reach that yellow straight line from the origin outward to the outer scale. The value, the point at where we stop, represents the location of the gamma plane of the input reflection coefficient gamma n. And we recognize that location to be a complex number whose magnitude is 1, since it's on the unit circle, and whose phase now is 90 degrees, is pi over 2. We may or may not care about that value. What we're really interested in is what is the input impedance. And so we want to transform that input reflection coefficient into the input impedance, normalized input impedance. And of course, that's very simple to do. We simply pick up our pencil and look at the intersection of our mapped impedance contours. All right, so we pick up our pencil and we look to see what contours intersect at that point. And we see, with respect to the contours of constant resistance, the R equal to 0 contour, which of course is the unit circle, intersects that point. And likewise, with respect to reactance, the contour that intersects that point is the X equal to 1 contour. And again, there's a typo here on the Excel Hero Smith chart. It should be 1, not 0.1 there. Once more, point out we have to be careful about the sign of that reactance. Is it positive or negative? We can't tell by looking at the number. We have to ask ourselves, are we in the inductive region or the capacitive region? And of course, clearly we're in the inductive region, so that reactance is positive. In other words, the input impedance that corresponds to this input reflection coefficient is 1 with the real part of 0 and an imaginary part of 1. In other words, an impedance of simply J, or 1 times e to the j pi over 2, however you want to express it. So that was another simple example of how we use the Smith chart to start at a load impedance and transfer back to an input impedance. Now, again, I used a relatively simple example where we knew what the right answer should be. We know how an open circuit transforms into different values with respect to its reflection coefficient. But I wanted to do something where you could know when you saw it that you knew was the right answer, and you understood the procedure and why we were doing it. Again, we don't want to turn our Smith chart into a series of recipes that we follow some procedure blindly, and it gives us the right answer, and we're not sure why, we don't care why, it's just all sort of magic. We'll do what the recipe says, and we get the right answer. Now, what we want to do is really understand what is the Smith chart, what are we doing, why are we doing those rotations, why are they circular arcs, in which direction do we rotate. All this makes perfect sense if we understand the Smith chart and our mappings from the complex Impedance plane onto the complex gamma plane.